Let's get started. All right. So today we're going to be talking about alkane chemistry, or the bonding, the synthesis, the structures of alkanes, stuff like that. We're going to be skipping naming alkanes purely because generally by this point most people are okay with it. They just need to practice more. If people watching this video are like, no, I want to have a lesson on it, let me know. We can set something up, but most people are good. What I did want to go over and start with is, since we are skipping the idea um, of just regular aliphatic straight chains, is, well, let me give you a couple of definitions to work with, because usually people are a little bit wonky about these words. Alkane chemistry. So you might see hang around in the textbook, or if you try to look things up and you really can't find it, is this word aliphatic. All right. And what I want you to know is that aliphatic just means what we can assume is something like a straight chain. Okay. So we're talking about something like that. You know, could we talk about something that has substituents? Sure. It doesn't have to be exactly a straight chain. But basically what we're saying is that we don't have resonance going on, all right? So we don't have tons of double bonds. We don't have things kind of getting in the way of the molecule. It's pretty plain as it was, all right? So if you see this word aliphatic, that's basically what we're talking about. We're talking about non-resonance. We're talking about just normal kind of straight change molecules. Likewise, you might see things like aliphatic chlorines or aliphatic alcohols. Again, explaining the same thing, that we're just saying that it's a regular molecule that's not really interacting with anything in terms of pi bonds. So with that in mind, let's take a look and let's talk about kind of the first flavor of kind of more complicated aliphatic chains, which is the cycloalkanes. So I'm a big believer that you can always take a word and break it down to figure out what it's talking about. So we have cyclo and we have alkanes. Well, we already know what alkanes are, and a cyclo group is just a ring, right? So what we're talking about here is a ring of fully hydrogenated carbons, or carbons that don't have double bonds going on. So what we're talking about here is we have, an infinite flavor of possibilities. This is where last night when I was working with the MCP kids, I was practicing doing these shapes. One, two, three, four, five, six, 7, and that's all I'm going to draw because I'm lazy. So as you can see, we have 3, 4, 5, 6, 7 carbons and on. We can have, technically an infinite number of carbons in the sequence. But what is interesting to know is that when we can talk about cycloalkanes as a substituent, but it's kind of interesting to talk of them as a group as themselves. And the first thing that I want to talk about is this idea about stability. Well, stability is all about being low in energy, right? Stable things are low in energy and they do not react. They are perfectly fine existing the way that they are. They're not going to, explode and kill someone. They're just going to hang out how they are. And so what I want you to know is that the most stable kinds of bonds, the most stable bond angle is at 109.5, right? 109.5 degrees. And again, that's describing that you have this central carbon, and on it, maybe we have 3 groups. And so this angle of 109.5 is how we describe this carbon. This is the natural angle for all sp3 hybridized bonds to try to get to. And by all means, they're going to try as hard as they can. But if we're talking about carbon, carbons can sometimes form bonds that aren't at that perfect 109.5. And so the closer to 109.5 you are, the better the bond that would be, right? So the question is, how do we get these bond angles, right? Let me just make sure that my reference is good. All right. Whoops, sorry. One more thing I have to look up. My bad. Ha ha ha. All right. So the name of the game is that we want to get to a bond angle of 109.5. So when we look at these ring structures, we can guess what these angles are going to be like, right? So we can see that this is a triangle. So this is going to be 60 degrees. This is a right angle. So it's going to be 90 degrees. This cyclopentane is going to be 108 degrees. Each angle in the cyclohexane is 120 degrees, and so on, right? We can go up and up, and we can talk about these things and their bond angles. So the question becomes, well, why does, what's the bond angle of cycloheptane? I can't remember. 360 divided by 7, whatever that number is. I don't know off the top of my head. So what I want you to know is that the bond angles closest to 109.5 are the most stable. And so that's going to be ring sizes of 5 and 6. So the vocab word that we're learning here is this idea about ring strain. All right. And ring strain is an increase in energy due to groups being at bad bond angles. Inside the ring. All right. So with that in mind, it's easy to see like, oh yeah, cyclopentane totally is going to be more stable than this 90, which is totally far away from 109. This 60 is too far off. And if I just divide out this 360 by 70 to get that, it should be, no, it should be, heptagon angle. What is it? 128.57. Believe this is 128 degrees. So the question becomes like, all right, we can see why cyclopentane is going to be a good pick, but why is cyclohexane? And so what we can do is we can look at what's called the heat of combustion. And so we measure the amount of energy inside of a molecule by burning it. So if we take any hydrocarbon, CxH2n plus 2, and we light it on fire, we take, maybe it's a liquid, maybe it's a gas or something like that. We apply heat and a spark. We just get it to explode. Think of gasoline. What we're going to get out of it is we're going to get our combustion products that you guys might remember from like high school chem or something like that. But more than that, we're going to get energy. And so what I want you to know is that the more energy in the molecule, directly translates to the more energy released. And we can measure that energy, all right? And this energy change is what we describe as the heat of combustion. All right, I know I threw a whole bunch of things down on the screen, so let me just reiterate what we're talking about. Well, I mentioned to you that these bond angles, that the most stable kind of bond angle is 109.5, right? And we've identified that we have two angles that are the closest to this 109.5, right? And so what we can do is we can measure the amount of energy to double check that our theory about stable bonds are low in energy is by measuring the heat of combustion. So we expect stable molecules to have very, very, very small amounts of combustion per mole, all right? Now, obviously, what we need to consider here is this idea about, well, if you have more carbons, that's more things to burn. So technically that's, more energy as it were. But what I want you to know is that we can measure specifically the amount of ring strain that's available, all right? So we can measure how much energy increase is because of the fact that they're at a bad angle. So if we take our cyclopropane, our cyclobutane, pentane, hexane, and heptane, maybe we want to take our octane as well. So these are our cyclo groups. And we can take the amount of ring strain, we can calculate it from this heat of combustion, all right? So basically what we do is we compare cyclopropane to regular propane, and we can take the differences between those, and we could say, okay, the additional energy involved is due to the ring strain. And we can extrapolate these ideas. So we have 27.6, 26.4, 6.5, 0, 6.3, 6.8, my bad, and 9.6. Oh, that's weird. Because if we look at the bond angle again, didn't we say that 109 was best? But here, hexane has less ring strain, has less energy due to the ring, despite cyclopentane being closer to the golden 109.5. Well, why? Why is having a bigger angle better than having a smaller angle? That doesn't make any sense, right? Doesn't that contradict what we're saying? Well, this is the thing. Molecules are not flat, all right? They are real things that exist in the real world. So even though we can draw them as polygons, they don't exist as polygons, all right? And this is the thing that gets students really confused, is they don't always understand that these angles exist in a what's it called? In conformations that need to be represented 3D. And so this is what brings in this idea about rings and how they have this 3D shape. And so essentially what I want to show you is just cyclopentane and cyclohexane, so we can talk about, well, why are those the stable structures, and then we'll extrapolate it from there. Okay? Are we making sense so far? Good, kind of makes sense, maybe review from the textbook. The big thing to know is that more strain, more energy, which is the name of the game that we're going to be talking about all day today, whether it's ring strain, torsional strain, there's another one, steric strain. So that's what it's going to be. So what I'm going to tell you is that flat molecules have more strain. All right, flat molecules have more strain. And the reason for this is because having that flat portion puts groups slightly close to each other, and they're kind of upset. All right. So if we take a look at, I'm not even going to attempt to draw these. I'm just going to have to show you what it looks like. Whoop. Maybe I can draw it. Let's try. For cyclopentane, let's take a look at the structure. The real 3D shape looks something like this. Where we have the 4 carbons down here, and then we peak this red carbon above the structure. And we can, the word that we're looking for is, this is called the endocarbon. Is that really important to know? No, maybe if you take Orgo 3 and 4, they'll talk about the endocarbon a little bit more. But essentially the biggest thing to know is that look at the bond angle here, right? That bond angle is almost practically a square, right? And we said that having that 90-degree shape was really bad. So even though that the total bond angles are really closer to 108, because this molecule is flat, it has more strain. All right. So this is what brings in this idea that just because bond angles are what they are doesn't necessarily mean what's going on is best. All right. Does this make sense so far? Cool. So what this does is it brings in a new kind of strain for us to talk about, okay? We talked about angle strain, and angle strain is about this idea about poor bond angles. But this idea about flat molecules allows us to define a new kind of specific strain, and that's torsional strain. It's this idea that the 3D shape of a molecule contributes to the additional strain or the additional energy within the molecule. And so what I want you to know is that cyclopentane, even though it has good bond angles, has very poor torsional strain, okay? Or in other words, that its 3D shape isn't that great. And this is what contributes for its higher energy, its higher ring strain.
Real quick, so how would you define torsional strain again? It's a little like Who's on the definition?
Torsional strain, it would be let me get the exact definition because I always get this one wrong. All right. Torsional strain is because of the close approach. Strain due to the close approach of groups within a molecule. That's kind of the general definition. But basically what I want you to know for this is that for this cyclopentane, when we take a look at the groups that are going on, what we notice is that the groups are fairly close to each other in the molecule. These groups here are pretty much parallel to each other, right? And what we'll talk about later, and then we'll come back to this idea a little bit more, because I want to talk about Newman projections and talk, because that's really where we see torsional strain. You guys have probably talked about Newman projections a little bit. But basically this idea that having groups that are lined up with each other is no bueno. And so it's this fact that because these groups are parallel to each other, that they have electronic repulsion, all right? Essentially that their electrons are not happy being near each other. But we'll come back to this in a second. The big idea that I want us to get is this idea about torsional strain is what is making flat molecules unhappy. All right, well, what's the mystery with cyclohexane? Why is it so beautiful? Well, before we dive into cyclohexane, I'm going to show you how to draw a perfect chair 100% of the time. Start with two lines that bisect each other. Two lines that bisect each other. Then you're going to go up, down, down, up. Perfect chair 100% of the time. Let's try it again. Two lines that bisect each other. Oop, drew this one a little bit too long. Up, down, down, up. Perfect chair 100% of the time. I will tell you this now, if you draw bad chairs, you will get points off. Every teacher does it. So if you have a written portion on your exam, I better see some good chairs, all right? So with that in mind, let's talk about torsional strain in cyclohexane. Well, the issue with that we describe with cyclopentane is that it has a flat portion. And that flat portion is contributing to the strain of the molecule. But what's happening with cyclohexane is that we're popping up one of the carbons on the right side, and we're popping down the other carbon. So if we take a look at the carbons that are parallel to each other, here's these guys. So we can start to see, oh, here's that square that would cause strain, right? But because we're popping down and popping up these carbons, we're completely relieving almost 100% of the torsional strain that's going on. All right. And if we wanted to talk about this, we'll talk about chairs more in a second. But what I essentially want you to know is that for these endocarbons on the end, that all of these groups are far away from each other. None of them are touching. And so what we're seeing here is a very unique structure that contributes to a huge amount of energy conservation. How do we feel about this? Does this make sense? Does this make sense why cyclohexane is more stable? So the question that you would be asked on the exam is, why is cyclohexane most stable cyclogroup? Or why is it more stable than cyclopentane? Or why does the 6-member ring contribute to a stable form? The reason has to do with the fact that it has little to no torsional strain. Okay. Cyclohexane has practically no torsional strain. Once again, why? Because it's able to pop these carbons up and down, and it's able to relieve this energy problem that's going on in this kind of square, flat portion of the chair. Does this make sense? Cool. Cool, cool, cool. All right. Another question that we like to ask all the time is, which is more stable? Cyclohexane or just regular old N-hexane? Which is more stable? Well, even though we talk about, oh, cyclohexane is super stable, everything like that, oh, it's so beautiful and everything, these bond angles are still not 109.5, right? Versus just a regular straight chain hexane, right? So these angles are 109.5. They are the beautiful angle that they can be. So N-hexane is more stable because it's not in a ring. Remember that even though the cyclohexane has little to no torsional strain, it still has some angle strain, which N regular straight chain hexane does not have. All right. So ring structures are always going to be higher in energy than regular structures for the most part. Are there exceptions? Sure. As you start tacking things on, you can change everything. But for the most part, that's what we're talking about. So these are the two most common questions that I see asked, and these are the two most common questions that people always get wrong. So kind of keep these in the back of your mind. All right. How do we feel so far about chairs and stuff like that? Good? Okay. If people have questions, let me know. If we need to do a review session about this the next time we meet, which I think is Monday, I can't remember, I'm happy to do it. Let me know. I'm happy to go over review again if we need it. All right. Um, uh, has she talked about oh god, what's axial and equatorial groups and everything like that?
Yeah, we talked about that in like the system train groups as well.
Sweet. All right. Perfect. This is my favorite section to talk about. Let's talk about let's dive away from the cyclohexanes. We'll come back to them. We'll also come back to that pentane portion that I was talking about as well, because we kind of did things a little bit backwards. But what we need to talk about is the Newman projection, which probably this and the Fisher projection are the two things that make students want to rip their hair out. But it's a very, very useful way about talking of atoms. Well, I hear you say, what is this Newman projection? The Newman projection says that if you are given any molecule like this, and what we're trying to do with the Newman projection was to try to discover what kind of strain is going on. And so what we're going to assume is that for these two carbons here, instead of looking at the molecule like this, where we're going to be looking at it from the front, what we're going to do is we're going to change it in our mind to be looking at it straight on. So it's like we're looking at the carbons directly here. Okay? So when you're doing this, and whether you're watching this video or you're with me right now, what I want you to do is hold the pencil up to your eyes, look at it flat and straight on, and then rotate it so that way you're looking at it from end to end. And what you'll notice is that if you close one eye to make things easier, is that if you're looking directly at the tip of your pencil, you cannot see the end of your pencil. And that's what the basis of the Newman projection is that we're essentially taking our eye and we're putting it right there. And we're training it to look at this carbon. And just like what we saw with the pen trick, is that we're going to be able to see that front carbon and the back carbon there. So if this is carbon 1, 2, 3, 4, 5, what's going to happen is that that third carbon is completely overlapped with the front carbon. And I'm just drawing a little border, even though it would be 100% overlapping. And so this is where we get that funky shape of the Newman projection from, is that we have overlapping carbons. With me so far? Sweet. So let me just clean this up a little bit, just so that way I'm not worried about this. What you notice is that if you did this to an actual molecule, what we're going to get a funky looking pattern going on, where we have the front carbon here, and then let me label the back carbon like this, and what we see is that we see the groups of the carbon 3 coming out of the spokes, but we can't see carbon 3 itself. Carbon 3 is hidden to our eye. And so this is what the Newman projection is. This is what it looks like. You guys have probably seen this in class by now. And there's a couple of things that we can talk about. What I want to do is I just want to populate onto the Newman projection the different functional groups that I see. So in carbon 2, which is my front carbon, I see a chlorine. I see a methyl group. And I know there has to be a fourth bond, which is a little hidden hydrogen that, let's say I'm going to put it there. Does it really matter where we're putting them? As of right now, no, but we'll talk about instances where it does when we go into things like isomers and stereochemistry and RNS. You haven't talked about RNS yet, right? No, it doesn't sound familiar. Con-angled prelog. All right. So once again, what I'm going to do is I'm just going to put the Br there. Maybe my hydrogen is there. And then this ethyl group, which either I can write as an ethyl group, like I can draw it directly, or what I like to do is I like to write ET. Could I draw it out? Sure. I could draw it as ET. ET stands for ethyl. Other abbreviations you might see is ME for methyl, PR for propyl, IPR for isopropyl, TBU for tert-butyl. So there's lots and lots of different abbreviations that we can use just because it fits better on the page. All right. Finishing up some definitions to know is that when you have two groups that are next to each other in the Newman projection, this is what's called a gauche relationship. Not gouch, not gouch, not gouchy, gauche. He's French. He has a nice French name. All right. But what do you notice is that one of the groups must be on the front carbon and the other group must be on the back carbon. So the question is, how many gauche relationships do we have? How many gauche relationships do we have? Well, we have another one here, and another one there, and another one there, another one here, and another one there. So we have 6 gauche relationships. in every Newman projection that's written like this. All right. Well, we have another relationship that we can talk about where we have two substituents that are on the different carbons but are opposite from each other. And so what we have going on is we have three of these relationships, and these are called anti. Is this making sense? Does this kind of review from class, stuff like that, a little bit? Yeah. Let me know too if I'm going too basic, and we can kind of speed through this a little bit.
So really quick, the anti just means they're like opposite to each other pretty much.
Exactly.
Okay.
Yep. God, I forgot to copy this thing before I ruined it. So let me just draw a new one. I see people all the time doing this where they make the circle huge and then they have like tiny spokes. We don't care about the circle. The circle is the least important part. So you can draw a small circle with big spokes. That's totally fine. Because what we care about is the substituents coming off of it, not the circle. So give yourself room. The last question that I like to ask people is just what's the relationship between this chlorine and this hydrogen? It's a trick question. There is no relationship between them. Why? Because they're on the same carbon. Okay? So relationships describe substituents on different carbons. Okay? So we can't describe the chlorine and the hydrogen with some sort of Newman projection relationship because they are on the same carbon. They are separated by that 109.5-degree angle, so they're not affecting each other. Does that make sense? Cool. Well, what's really interesting about single bonds is that, as you probably learned in class, that this bond can actually rotate. Boop. And I believe at room temperature, it rotates about 10 to the 15 times a second. So this thing is rotating really, really, really fast. It's spinning around just like a pinwheel, all right? And so this conformation doesn't always survive. Like it doesn't always stay here, for all eternity. So what can happen is that this can convert into the next kind of conformation. And what happens is essentially I like to rotate the back carbon. It's really up to you what you prefer. And let's say that it's doing a half turn where the back carbon and the front carbon are overlapping. All right. And so essentially what I want you to think about is that the back substituent is completely overlapping with the front substituent. So it's like we can't even see them. We can't see the spokes that they're on. And so because of that, what we generally like to do and what I will do just because it's easier for me to draw is you'll see me do this. Just kind of draw it off to the side. That's all it is. But what we're doing and we're thinking about in our heads is that it's in fact completely overlapped. So whatever for you easier on your page. So I said I kept the front carbon the way that it is, so I'm not going to change it at all. And I rotated the carbon a half step. And so what this has done is it's come up with the two different conformations. Conformations. All right. And there are two different kinds of conformations. There is the staggered conformation and the eclipsed conformation. All right. And in the eclipse conformation, do we have any gauche relationships? No, we don't. Remember that this gauche relationship is what's described as kind of the spoke in the middle. And if we wanted to, we could describe it with an angle, which is 60 degrees. The angle that's going on between these two functional groups is 0 degrees, even though I've kind of written it with a little bit more of an angle. But don't forget that eclipse means completely overlapped, so that angle is 0. Well, the question is, do we have any anti-relationships? Nope. Once again, everything is eclipsed. So what should be opposite this hydrogen is missing. So in eclipse conformations, we only have eclipsed relationships. So for, once again, in eclipsed conformations, we only have eclipsed conformations. And how many do we have? We have 3. And again, if we wanted to talk about the angle for anti, the angle for anti is 180 degrees. All right. With me so far, is this making sense, everything like that? So here's the thing. These different relationships contribute different energy levels to the Newman projection. And essentially what I want to tell you is that gauche relationships, that of the 3 relationships, I should say, an anti-relationship is lower in energy than a gauche relationship, which is still lower in energy than an eclipsed conformation. And let's think about why, all right? If you think about these groups as like hands, all right? What's happening with the anti is that they're away from each other. And so when these things kind of wiggle on their own, what happens is that they're not hitting each other. And because they're not hitting each other, they're not interacting, which means they're not having any kind of electronic repulsion, meaning their electrons aren't interacting. And so they're not going to have any energy, any energy, what's it called? Interference. So if you have anti-relationships, those are not contributing to the strain of the conformation. Gauche relationships, however, it's kind of like you have your hands like one like 90 degrees and one up above, and sometimes they don't hit, but then sometimes they do. And it's when they do is where we start to see the strain happening. So which is why gauche is more in energy, and why eclipse, where the hands are completely sort of, what's happening is that these things are hitting each other almost 100% of the time, and these are the highest in energy. All right? So one of the things that you'll have to do on your exam is you'll probably have to construct a what's it called? A stabilization or a energy diagram, right? Has she talked about energy diagrams? No, she didn't have you do something like this and you had to draw a line that was like, yeah, she did have you do that? Okay. So let's say that we're given let's say that we're taking the same group here, all right? And so let me show you how you're going to set up your page first. Actually, let me just copy this. It'll be easier. So for this molecule that we're given, how I want you to set up your page is kind of like this. So you might need a new page. It's up to you. What we're going to have is we're going to have 6 circles written like that. And then somewhere off to the side, leave yourself room for like a big graph. So if you wanted on your piece of paper, it'd be something like, here's your 6 circles, and then, the graph like that. All right. Well, let's just grab that first conformation that we were talking about before, which I've already forgotten. BR HET. And what we're going to do is we're going to rotate this back carbon a half step every time. I'm actually going to need more room. Just because I write huge. And so what we're going to see is that every time that you rotate from a staggered conformation and you do a half turn, we're going to end up in an eclipse conformation, right? So the half turn here, Cl, CH3, this is, staying the same. We're keeping the front carbon the same. Rotating this, so now the H is behind, the Br is behind, and the ethyl is behind. Do another half turn, and if you look, we end up at another staggered conformation. Do another half turn as we're just going around. We can start to see how the pattern emerges, and we can just kind of fill these in. And then finally, at this last conformation, what we'll notice is that if you do another half turn, you end up at the start. That's what it is. And what we can see is that, A turns into B, B turns into C, C turns into D. So we can start to see, that this is what's going on. I'm just going to leave out these arrows just because I don't want it to get too complicated as we're looking at this. So what we can do is we can start talking about this torsional strain. Now go back to that definition that I told you, right? Torsional strain is all about strain that's due because of close approach of groups within a molecule, right? So what do we think? Do we think staggered conformations or eclipse conformations are going to be higher in energy?
Eclipse.
Going to be eclipsed, right? Because we have the groups directly overlapping each other, and these things are going to be smashing into each other. And so if they're big and they're big and bulky, they're going to contribute more to the torsional strain. All right. So what we can do is we can make a graph that shows how the energy in the molecule changes as it rotates around the axis. And what we'll notice is that small groups that are overlapping are going to be the lowest in energy, all right? Whereas large groups overlapping are going to be the highest in energy. And so what do I mean by large? I mean big atoms with lots of electrons, all right? Or I mean really, really bulky things like a tert-butyl group, all right? So if we look at our conformations, already hands down, we know that eclipsed is going to be higher in energy, right? So we can just take a look at which of these three is going to be higher, right? Highest. So what I would say is that probably F is going to be highest in energy because we have chlorine and bromine overlapping, right? Versus this ethyl group is overlapping with a tiny little tiny hydrogen, and this hydrogen is overlapping with a small methyl group. So we're probably not contributing a lot of strain here. But we have, if we wanted to draw ourselves a little diagram, maybe here's carbon, here's chlorine, and here's bromine, right? So these things are massive, they're huge compared to each other. So them overlapping means that they're probably going to be highest in energy. Does that make sense? Cool. And so what we know is that as we spin out of F, we're going to end up at A, and that A automatically is going to be lower in energy than F, right? Hands down, because it's in staggered. And so staggered conformations have to be lower in energy than eclipsed. So, maybe we put it there, like halfway down or something like that. Now we go from A to B. B is going to be higher in energy because it's eclipsed, right? Has to be higher in energy. But is it going to be as high in energy as F? No, because we identified F has the biggest overlap. So, maybe B is right there. Then we take a look at C. We spin into C, and what do we notice? Oh, now our big bulky groups, the big thing that was contributing to energy, are anti to each other, right? And what did we say about anti? Anti groups do not interact. They don't add to strain. So C is going to be the lowest in energy. Then we spin into D. And what we notice is that D is actually the same thing. Wait, C to D. Am I crazy? What we notice is that D is going to be higher in energy than C, but it's probably going to be in slightly less energy because now we have these hydrogens overlapping, right? And these aren't really going to interact with each other. Hydrogen is tiny, so maybe there's slight interaction, but there's not. So, maybe we're going to put D like slightly below. We don't really know what the numbers are, but we know that it's at least going to be higher than A, right? Because A is staggered. And then finally, we're at E, and we know E is going to be less energy than D, so maybe it goes there, for instance, could we say it's going to be higher in energy than A? Sure, maybe. But these chlorine and the bromine are still gauche to each other. But maybe it's less in energy because now the ethyl and the methyl are anti versus here they're gauche. So maybe it's not exactly, maybe it's, slightly less in energy, something like that. Well, this is all well and good. Oh, and then of course we spin from E into F, and we know F is the same thing, right? And so what I want you to notice is that we have this graph being made. And what we see going on is that the molecule is going from places of high energy to low to high to lowest to high to low to highest. And so it's constantly going in this undulating fashion where it's going up and down, up and down, up and down. All right. And so we can ask the question, will a change be spontaneous or not? All right. So let me just redraw that graph down below. Just actually, I can copy it. I really need to start copying things more. Is that going to work? Yeah, there we go. And so a question you might see on the exam, this is a really common thing that I've seen in years past, is the transition from F to A spontaneous? Well, to be spontaneous, it means that we need to release energy, right? Because spontaneous reactions are exothermic. They release energy from the structure, all right? So is going from F to A spontaneous? Does this release energy? Yeah, it does. So this is a spontaneous reaction, or a spontaneous transition, I should say. All right? All right. Is going from A to B spontaneous? No, it's not, right? We have to go up in energy, right? And a molecule is never, ever going to want to increase in energy spontaneously. That's not going to happen. So what do we call when you have to go up in a hill? There's a specific word that as soon as I say it, you're going to be like, oh my God, I know, I knew that. Anybody have an idea? It's activation energy. Yeah, right? Oh, it's that thing from Gen Chem, or oh, it's that thing from high school chem, or something like that. That's all it is. Whenever we go up in energy, from the bottom of the hill up to the top is just the activation energy. And needing an activation energy is not spontaneous. Okay? All right. How about going from F to C? Is this spontaneous? What do we think?
F to C.
F to C, yeah.
Yes, it's going from high to low.
We would think, right? And so this is the interesting thing, that it could be spontaneous, but most of the time I believe that they're not.
Oh,
And the reason is because, yeah, we're releasing energy, but then we have to gain energy again. And even though we might be releasing more energy than we have to gain, we don't know that that's entirely true. So whenever you go up in activation, we're decreasing the spontaneity of the reaction or the transition. So my bet is that this is going to be a non-spontaneous transition, all right? Even though that it results in a more stable molecule, something lower in energy, we're still going through an activation energy, and that activation energy is going to cause a rate limiting step. So a good question on the exam is, for the transition of F to C, what is the rate limiting step? Well, what we can do is we can label the different steps: F to A to B, B to C. And spontaneous steps aren't going to be rate limiting, because these are just, they're favored, right? They're going to happen. Versus this A to B transition is non-spontaneous because it's unfavored. And so this is going to be the rate limiting step. By the way, if you're wondering what a rate is, the definition, I don't think this is the actual definition, but a rate is just, what I like to think of it as, the time for the reaction. Reaction is shorthanded to Rxn, by the way, in case if anybody is wondering. So basically what it's saying is that what is the step that's causing the reaction to take longer? And it's because we have an activation energy. Really common question to see. How are we doing so far? Does this make sense? Good. Cool. Big thing about Newman projections, the hardest thing is just making sure that we're just producing things on the right carbon. So when we create our Newman projection, all of the substituents on the front carbon have to be on the front carbon, all the ones on the back carbon. We can practice more of this on Monday, but I kind of want to get the theory out of the way today, because the theory is what ends up screwing people. Cool. Good with kind of regular Newman projections so far. Any questions, anything like that? Good. Cool. All right. Is this more clear than maybe lecture or the textbook, by the way? Yeah? Okay. Well, I had told you that we were going to come back to that question about torsional strain, right? About cyclopentane. And just to redraw cyclopentane for us, we see that we have this this carbon being popped up above, and that the endocarbon is relieving some of that strain because it's up here, right? Versus these 4 carbons that are oh so lonely, stuck down at the bottom. What's interesting is that we can make a Newman projection. Here's my little eye. And I can look down this bond here and see why does cyclopentane have that torsional strain. And, maybe I'll label the back carbon in pink just so that way we can see it. What we notice, here's the front carbon. Is that the front carbon and the front carbon and the back carbon, whoops, I drew this the wrong way, are eclipsed. So, if I wanted to label this carbon A and this carbon B, A and B are eclipsed. And so this is why, even though that the bond angle in cyclopentane is very good, we have tons of torsional strain because they're eclipsed. And what we saw is that eclipsed molecules always have more energy than gauche or anti-relationships. All coming together, right? Okay. Well, let's take a look at that cyclohexane one more time. Again, if you want to draw a nice chair conformation, 2 lines that bisect each other, up, down, up. And what I want you to notice is that for our carbons that are within the parallel side, what's interesting is that if we label what the substituents are doing, so, here's the pink carbon substituents, and here is this green carbon. If we take a look at the Newman projection that's going on, what we see going on is that the relationship between the green and the pink carbon, or, if we wanted to talk about the green and the yellow carbon, or any carbon on here, all of the carbons in the cyclohexane are in the staggered conformation. Is this a real staggered conformation? Kind of. I believe that this angle is like 55 degrees. So, not the perfect 60-degree gauche angle that we want, but good enough, So what we're describing here is that another reason why cyclohexane is so stable is because it is able to have that staggered conformation, which, as we know, is more stable than otherwise. How do we feel about this? Good? Cool. Let's take a look at axial and equatorial groups, because this is probably another thing that ends up getting people a little bit funky is they don't really get axial versus equatorial and how those contribute to the heat of formation of cyclohexane. Has she mentioned heat of formation, delta H? If not, we're going to talk about it because it's important to know and it kind of clues us in on some other things as well. I did the midnight tutoring for MCPHS last night, 8 p.m. to midnight. And oh boy, was that fun. So when you guys have your exam, let me know the night before. We'll do a midnight tutoring as well. Although your exams are on different days, so we're only going to do one day though. So because I can't sacrifice that much time. All right. Axial versus equatorial. I'm also going to give you a cheat sheet, which is probably the only, the one thing that students love and like they have hands down like praised me for is this little cheat sheet that I came up with. But essentially, we're going to be talking about axial versus equatorial positions. So if we have a chair, what I want you to know is that every carbon, and I'm just going to alternate the colors here. Oops, I did it wrong. Just going to alternate the carbons for us, just so that way we can talk about them. Every carbon has an axial and an equatorial group. Every carbon in a chair has an axial and equatorial group. And so what we're going to be talking about here is axial versus equatorial, but then this idea about a up carbon versus a down carbon. All right. If we say that this red carbon here is up, you know, maybe this one is up. Well, the next carbon must be a down carbon. This is the pattern that I'm telling you that is true. How do I know that? Well, if I want to talk about it this way, I have to draw myself down, going down to get to this green carbon, down, down, down. So that makes it a down carbon. I actually have to move. I can, no, I have to move them. Up, down. All right. Same thing. If this is an up carbon and this is a down carbon, then this carbon here must be an up carbon as well. And what we're going to see is that this pattern repeats itself. Up, down, up, down, up, down, up, down. And so what we end up with is 3 up carbons and 3 down carbons. And what I'm going to tell you, wow, that's a bad chair. Wow, this is also a bad chair. Is that for up carbons, their axial position faces straight up and tall, and the equatorial position faces out. Whereas for down carbons axial group is down and tall, down and proud, I don't know, and equatorial. For this inner up carbon, this one that's kind of in the armpit, I like to draw the equatorial going up and through the molecule. And then we draw the equatorial group coming out kind of into the armpit of the molecule. Next, we're at a down carbon, so we're going to have equatorial and down axial. Then we have an up carbon, so this is up equatorial and up axial. Sorry, up axial is this one, and up equatorial is that one. And then finally, for this one, I draw the group coming down, kind of through this, and then again coming into the armpit of the molecule. Hopefully yours looks more pretty than mine does. And so this is what we're talking about. Up carbons have an equatorial and an axial group. Down carbons have an equatorial and an axial group. Are these two positions here, are they still gauche? Yes. Yes, they are. Equatorial groups are always gauche. Okay? Equatorial groups are gauche. So is this one that I'm labeling with yellow, is that one gauche to that one that I'm labeling yellow? Yeah, they're adjacent equatorial groups, so they're still gauche. So don't get confused. These two are gauche to each other, but if I label this one orange, is orange gauche to yellow? No, it's way too many carbons away. We can't describe that with a Newman projection. So equatorial groups are gauche versus axial groups are anti. Cool. So just like how we saw with Newman projections, these equatorial groups, if they're very large or if they are very bulky, are going to contribute to some, torsional strain. So while a regular cyclohexane by itself doesn't have torsional strain, as we start adding more and more functional groups, what we're going to see is we're going to increase the torsional strain. So let's say, for instance, I had a chair where I had an isopropyl group there, and I had a, I don't know, like a methyl group there. Would this be high in energy? Totally, because these two groups are gauche to each other, and so they're going to contribute to a to higher in energy. Okay. Here's the interesting thing, though. Remember how I said that hydrogens don't really interact with each other? So, for instance, that if I had a hydrogen there and a hydrogen here, their orbitals are too far away that they're really not interacting. Versus maybe for, these two groups, maybe they're overlapping like that, and so they're kind of banging into each other and getting upset. Here's the interesting thing, is what I'm going to tell you the rule is that equatorial groups, or let me put it this way, having functional groups in the equatorial position is always, well, I shouldn't say is usually, I mean, are there exceptions? Sure. Is usually more stable than axial. But wait, I hear you say, why is that true? We just said that these things are interacting and they're going to be upset. Well, the interesting things about chairs is that they can undergo the chair flip, which is essentially where the molecule rotates, and what happens is we end up getting a new conformation on the chair. All right. Now, I just want to segue into how do we do a chair flip, and then we'll come back to this idea about why this is more stable in a second. So let's say if we have, a chair that looks like this. God, I'm not doing good with my chairs today. And let's say that I label this 1, 2, 3, 4, 5, and 6. What's going to happen is we're going to push this carbon down, and we're going to push that carbon up. And what we're going to be left with is the chair flip. Whoops. where this carbon here is still carbon 4. Carbon 4. Yeah. And this carbon here is still carbon 1. Counting all the way around, we can fill in the rest of our numbers, 1, 2, 3, 4, 5, 6. And what do you notice? That our carbon 4, which was originally a down carbon, has now been converted into an up carbon. Our carbon 5, which was originally an up carbon, has now been converted into a down carbon. And so what you see is that when you perform a chair flip, we have converted all of our up carbons into our down carbons. So for a chair flip, all of our down carbons get turned into up carbons, and all of our up carbons get turned into down carbons. Likewise, all of our equatorial groups have now become axial groups, and all of our axial groups have now become equatorial groups. All of them. So let's say, for instance, maybe carbon 1 had a methyl group in this equatorial position. Well, now this methyl group is going to be axial. All right. So when you draw your two conformations of a chair, you have to make sure that you're also flipping the position that the functional group is found in. All right, now that we've talked about chairs and I'm happy with that, let's go back to this idea about why is axial higher in energy than equatorial. Let's take a look at our example again. We said that in the equatorial position that maybe these groups are interacting with each other and that their orbitals are overlapping and causing strain. We perform the chair flip and maybe to make things easier, I'm going to label this carbon 1 and carbon 2, 3, 4, 5, 6. So if this up carbon now becomes a down carbon, then this is 2, 3, 4, 5, 6. All right. Now our methyl group is now facing right down. And now our isopropyl group is facing straight up. Oh, but didn't I tell you that adjacent axial groups are anti? And anti is low in energy, right? So shouldn't this be lower in energy? Why are you talking about this? Like, what are we talking about? Why, if these guys are lower in energy in this conformation, why are we talking about this rule up here that having groups in equatorial is usually more stable? This is the reason. That remember that I said that all the up carbons are going to have groups that are axial as well. And so what's happening is that all of these hydrogens, all these axial groups are going to be interacting with each other. All right. So yeah, maybe our functional groups aren't interacting with each other, but now these things up here are. And this is what's called a 1,3 diaxial interaction, or also sometimes called 1,3 diaxial strain, 1,3 diaxial instability, different things like that. Same thing over here, our down carbons are also going to have, maybe some hydrogens hanging around. And what we notice is that these are going to be interacting as well with the methyl group. My drawing's a little bit bad, but. And so this is also going to be a 1,3 diaxial interaction. It's almost like what we've done. And if we drew the Newman projection of it, where we're kind of looking at the 1,5 angle, it's almost like we've doubled the number of, what we've done is now we've eclipsed the methyl and hydrogen. Or what we've done is we've eclipsed the isopropyl group and the hydrogen. Oh, that's why it's bad for strain, is because now we're talking about eclipsed, and eclipsed is terrible in terms of stability. So this is why the rule about functional groups in the equatorial position are more stable, because they're not eclipsing each other, all right? So whenever you're on an exam and the question is, please circle the chair conformation that is most stable, we want to be putting our big bulky groups in the equatorial position. All right. So what's an example of this? Well, let's say that we had something like that, and we perform our chair flip. Let me put these in colors for us just so that way we can see what's going on. And I think I had one here. And so the question would be, which is more stable, A or B? And we would say, okay, here we have 2 equatorial groups and 1 axial group, versus here we have 1 equatorial group and 2 axial groups. So of course, A is going to be more stable. All right. Equatorial is always better than axial, hands down. Right? When in doubt, go to the mother rule. Are there exceptions? Can you start, tweaking things and saying like, well, technically the energy of this in one regard is, yeah, you can come up with these different examples of where you have exceptions to the rule. But this in general points you to when you have simple substituted cyclohexanes, this rule is true. Equatorial is more stable than axial. Cool. Any questions from you so far? No?
Explain how you drew like the hydrogen, like the green one, and how it became the B, from like the A to B.
Like how did the red line became like this? Yeah. So let's actually let me copy this. So the question is, how did this red line turn into that red line? Like how did this happen? Well, I always like to just number things as I want, Does it matter where you put the number? No. I usually like to put it in the top right position just because that's where I'm most comfortable. do whatever you would like as long as you stay consistent, okay? If we do a chair flip, what we're going to be doing is we're going to take this carbon, we're going to push it down, right? So another thing that we can check to make sure is that right now, this carbon is up. And so we better make sure that when we label our 1 over here, that it is a down carbon, which if we look, it is a down carbon. So we're all good. Now that we've tracked where our 1 is, now we can just label going kind of clockwise. And what we see is that, okay, this is how our numbering is. And so we can talk about how this is an up carbon, this is a down carbon, up, down, up. Same thing, we can do down, up, down, up, down. And so all this is doing is just helping us make sure that we're tracking things the right way. So carbon 1 was originally an up carbon. Now it's a down carbon. Oh, I see what I did wrong. This should be on carbon 1. Oops, ha ha ha. It should be right there. That's where it should be. My bad. So carbon 1 is going to have that methyl group. And so it was originally in the axial position. And so when we do our chair flip, we have to make sure it's in the equatorial position. Carbon 2 doesn't have a functional group. Carbon 3 was originally equatorial. Now it's in the axial position. And how do I know it faces down? Well, it's a down carbon. And so I know that it would be an axial down. And then finally, for this 5, it was originally equatorial. And now it is on a down carbon. So it's going to be axial. Does that answer your question? Cool. Cool, cool, cool. All right. What was the other thing? Do you have to know how to name bicyclic rings? So things that are like that? No? Okay.
Well, we have to know something like the chair stuff, like boat and like twisted boat of cyclohexane.
So with that idea, the best way to describe that is with a picture, because that is way beyond my drawing capability. Can you see the screen over here? Yeah? Okay. So what this picture is describing is the chair flip and what happens when we are converting between chair and chair. So I mentioned to you that we're pushing down on one side, pushing up on the other side. It would be really great if we could just do that in one go. But what happens is that we have to enter in through these kind of what are called half chairs in this boat conformation. All right. So what it is that when we push up on this side, as it's being pushed up, up, what we see is that it goes up in energy because we're essentially making this portion. Can you see my pointer, by the way? Yeah, okay. We're making this portion on the left side more and more flat. And just like we talked about with cyclopentane, that when things are flat, things go wrong. And what you notice too is that look at these axial groups. These axial groups are almost eclipsing each other. If we would take a look at like a Newman projection and kind of shift ourselves. Same thing with these equatorial groups is that they're all starting to eclipse each other. So that's why we're going up in energy. Likewise, what we see going on is that as we finish pushing this up all the way, what happens is that both of these groups are now kind of facing up on the molecule, and this is what boat is. Sometimes it's referred to as twisted boat, sometimes it's just regular boat. Honestly, they're both kind of describing the same thing. But the big important thing here to know is that these axial groups here, these two guys at the top, they're interacting in a 1,4 diaxial interaction. Very similar to the one that we described earlier about 1,3. In fact, I can show you right here. Here's this boat conformation, and you can see that what's called the flagpole interaction, or that we have a 1,4 diaxial kind of torsional strain. Twisted boat is kind of the same thing, except we still have this torsional interaction. It's just that we have less strain on the arms of the boat. As we push down the other side, we start to push it down, and what we do is we make this portion a little bit flat, which is why we push it up to this half chair, and eventually it gets pushed down and we're at the other chair. So another way of looking at this is, you know, we're pushing up and up and up, and we're getting to this boat. Then we're the boat needs to kind of relax some of that planar function of what's going on in the middle here. And so what it does is it kind of twists itself to relieve some of that strain. And in the process, it ends up pushing down the other side. So you can kind of see that a little bit more, that as the boat comes out of, fully all the way up, it's kind of entering this slightly more stable conformation before it, shoots right up in energy, because it's getting into that half chair where it is almost looks like cyclopentane. So that's the big thing to know. Generally, we don't have students draw twisted boat or boat because, I mean, it's hard enough to show chair correctly. These are computer generated, so it's like nice and prim and proper. But it is what it is.
But wouldn't like the boat be most energy than like half chair? With both facing up?
Good question. And the reason that it's not has to do with, again, let's see if I can find a good picture of half chair. Is here we go. Is because this, starting at this carbon, this one, this one, this one, this one, all of these carbons here are completely flat, or almost completely flat. So just like how we saw with cyclopentane and why cyclopentane is unstable because it's flat, it's the same thing going on with half chair. So even though, yeah, in boat we have kind of the two portions going up, but we have less planar function to the molecule, is what that is. Does that make sense? Good question. Good question. All right. Here's a really good diagram. So again, twisted boat is slightly more stable than regular boat, purely because we're just relieving that planar function of the inner portion of the boat by just kind of twisting it a little bit. But obviously, if we look at the potential energy going on, the chairs are the most stable conformations. God, I wish I could draw like this. If I could learn to draw like that, that would be amazing. I should take an art class. Cool. How do we feel about that? Good. Sweet. If anybody who's watching this later on has any questions, I would recommend coming to the Monday 9/28 session that we're going to do, or send me questions. I can, if you send me questions and if I have time this weekend, I might put together a video that just kind of explains them all. If not, I recommend coming to that session that's going to be in a couple of days, or reach out. I'm here to talk about it. Cool. So we covered a lot of material today. We didn't do a lot of practice purely because my viewpoint with tutoring is that you'll find that I spend a lot of time explaining theory and how things come about, almost like a professor would, that they are explaining kind of the bulk of everything. So as you continue in the semesters with me, you'll find that I don't do a lot of practice problems, mostly because there's thousands of YouTube videos about how to do practice problems. I'm sure you have SIs and TAs at your school that provide recitation sessions. Um, but there are not a lot of resources that are out there that sit down and teach you the material in another way. So if you ever are out there, people who are watching this, you're like, wow, I wish Gabe did more practice problems. I have them, but you won't see me using sessions to really go over them that much because there is just so much material to go through, um, and stuff like that. um, cool. Is there any other part of chapter 3 that you can think of off the top of your head?
Did we go over how to like find cis and like trans?
Yes, we can totally do that. And again, she hasn't talked about R and S yet, right? Okay, cool. Sweet. All right. You can see the drawing screen, right? Cool. All right. Cis versus trans. So cis and trans is a really kind of integral part of again talking about this idea about not torsional strain but almost steric strain. So remember that I said that torsional strain was because of the too close approach of functional groups, right? That's what we had talked about. But what I want to do, and I want you to be aware of, is that all of the molecules that we talked about so far, whether they be chairs or whether they are the straight chain molecules, what can they do? What do straight chain molecules and chairs do that a double bond would not be capable of? So say if we have a double bond like this, what can this molecule do and a chair can do that a double bond cannot? And the answer is rotate. Chairs and straight chains are able to rotate, whereas this double bond here is locked. It cannot rotate. There is no rotation possible. Okay? So what you can kind of think about, and this should make sense, is that torsional strain is because of molecules that are too close to each other, and then we see that we rotate out of it, and then they're far apart, and then we're nice and stable, right? So what you can amend to your statement and kind of think about in your head is that torsional strain is really referring to the too close approach of functional groups in rotating molecules. And what I want you to know is that torsional strain falls beneath, I believe this is true, a more umbrella category, which is steric strain. Is it fair to say umbrella? I believe it's fair to say umbrella term. I think there's other kinds of steric. So in a way, we could say that torsional strain is a more specific kind of steric strain. And what's steric strain? Well, steric strain is due to strain. Let me get the actual definition so I'm not. Steric strain is just this general statement. It's the strain due to overlapping orbitals of close functional groups, FG. So it's this first part of the that we learned about torsional strain. And so maybe this is a little bit confusing to learn it in this order. That's a little bit my bad. But just to clarify again, torsional strain is a specific kind of steric strain in which you have steric strain, so functional groups that are too close, but then we can rotate the molecules so that way we're relieving that strain. All right. So torsional refers to rotating molecules, whereas steric strain, whereas torsional strain cannot refer to double bonds. All right. Does that kind of make sense? It's kind of like the rhombus in the square kind of business. You know, all torsional strain is steric strain, but not all steric strain is torsional. You know. There's a really good chart out there. I think it's on Chem Libre that explains steric strain really nicely. But back to this idea of cis and trans. Cis and trans was kind of this way of describing the relationship between substituents on double bond. And what cis means is same side, whereas I wrote train. Trans, what am I doing? Trans refers to opposite side. So if we have a group that's like that, or if we have a molecule that's like this, or if we have a molecule that's like that, what we can do is we can start to describe these molecules in a in describing cis and trans. So the way I like to go about it is I like to put a dotted line perpendicular to the double bond. And what I like to do is I like to look at the molecule and I like to say, okay, sorry, not a perpendicular. Ha ha ha, my bad. Parallel. Perpendicular is the next thing that we're going to do. And I like to say, okay, are the functional groups facing on the same side or are they on different sides? And so if they're on different sides, we're going to describe this as trans. So once again, we're putting a parallel line through the double bond and we're looking at each side. Same thing here, put a parallel line through, and what we see is that both of these groups are on the same side, and so this is a cis bond. Can this molecule rotate? Well, this portion could rotate. That's totally fine, but this portion is locked. Well, how about this cyclohexane? It cannot rotate because it is locked. Okay? So in order for a cyclohexane to rotate, it needs all of its bonds to be free. So this is a trans molecule, this is a cis molecule. What about this guy? What is he? Well, we can see easily that this bond is cis, right? And that this bond is trans. But what is the molecule itself? It's cis-trans, or maybe it's trans-cis. We don't really know, right? So I'm going to give you a little insight into what you're going to learn for next exam is this issue about having multiple bonds that might be different. We're going to learn a nomenclature system that's going to allow us to describe these kinds of bonds. And so because of this description of bonds, we're going to be able to talk about kind of what's going on. Does that make sense? Was this what your question was?
So my class, like the professor was talking about like the cis and trans, like not just on a double bond, but like single bond, like cis 1,2 dimethyl cyclopentane or something, and then like,
Mm-hmm.
and then the H's like that goes up in the same direction, they're like cis. And then the methyl group that goes down in the same direction, it's like, that's also cis.
Did she draw something like this?
Show you.
Yeah, if you want to send me a picture, if you can.
Can you see this?
Ah, I see what she's trying to do. Okay. All right. Wait, show me one more time.
There's a whole thing.
Ah, okay. Cool. I see what she's trying to do. Sweet. So, another way that we can describe molecules is by using what's called the hashing, or sometimes it's dashing, the dash and wedge system. And basically, the reason for doing this is just because when we are talking about molecules and we're writing them on a piece of paper, we draw them 2D, but molecules are 3D. So we want to be able to describe what's going on. So if you see a bond where you have this filled in triangle, we're talking about a molecule, the functional group is coming towards us. So it's like it's popping up and out of the page. Versus if we see this dashed line, which I draw terribly, looks like that, then the functional group is moving away from us. So what your teacher is describing there is, let's say for instance, we have a functional group like this. Is this molecule cis or trans? All right. The answer here is that they're cis. The reason why is because even though these things are on the, technically the top and the bottom of the molecule, remember that these represent a 3D-ness to the molecule. They represent coming in or out of the page. So what we're saying here is that both of these molecules, if I wanted to draw it, like here's my sheet of paper. Here's the straight chain portion. And essentially what I'm saying is that both of these chlorines are sticking up and straight out of the molecule. They're like above the plane. So they're like sticking straight up like that. Both of them. And because they're both sticking up and out of the plane, this is a cis molecule because they're both on the same side of the molecule. Same thing if we wanted to describe the opposite, but now a trans molecule. What's going on here is that we still have this same chain, but now what's happening is that we have one chlorine that's coming straight up and out of the page, but then we have another chlorine that's coming down and through. So it's like it's going shooting right into and through your table, or it's coming down like that. So we have one that's up above and we have one that's down below. And so they're on opposite sides of the molecule. So this is a trans molecule. To explain what's going on with like a cyclopentane, this line is just showing, it's kind of terrible. Let me try drawing it again. There we go, that's a little bit better. To describe what's going on here with this cyclopentane is we have maybe this hydrogen here and this hydrogen here. And maybe we have, a chlorine going down and a chlorine coming down. All right. And so what we can say is that both of these hydrogens are above the, the square portion, this planar portion of the molecule. or both of these chlorines are both below. So this would be a cis molecule as well because they're both on the same side of the molecule. Same thing if we wanted to describe a trans molecule, whereas maybe we have one coming above, one coming below. And so what we can see is that we have now a trans relationship. Now, I hear you saying, well, what about cyclohexanes? We're going to come to cyclohexanes probably next test, right? She didn't talk about cyclohexanes yet in terms of cis and trans. At least not in a chair conformation.
But I did see like a practice problem. So
Let me show you what I might be talking about. Did the practice problem look like this, or did it look like a chair?
the practice problem was like looking like that, and then it had like a bunch of stuff coming like up and down. And it was like, oh, which of the atom is like cis to this atom, or which of the atom is trans to?
Okay. If you want to find that problem for me and send it to me, because I might save that for Monday, just because what we do on Monday will probably be closer to that. Just to explain this thing in case of people watching the video couldn't understand what my writing was, just explaining that, this, if both of your BRs are on the top of the molecule, then we can call this cis. And if one is on top but one is on bottom, then we can describe that as trans. So that's really all we're describing here. That's all it is. Same thing that if we can see the wedge here, dash there, trans, both wedge or both dash, then that's cis. Cool. Let me check as well. When's this exam? 10:02 and 9:30. So that's kind of cutting it close. And you guys have chapter 4. All right, that's what I'll do. So what I'll do is this weekend I'll come up with some notes about just some extra things that I want you to know about. Maybe I'll record it into a video if I end up having time. I'll send out a message on Snapchat about, which one of you guys, if people want to attend that recording or not, feel free. But again, we can see kind of the relationships of cis and trans here. Cool. So I'm going to stop the recording here.